earlier already is that we can start tuning the knobs. For example, we can change the external torque that we apply by changing the strength of the electric field. And we did exactly that. In the plots here, I'm showing you number of stator units as a function of time, averaged for different conditions over 162 bacterial cells. And what we did was that we changed the electric field to drive the rotation at different electrorotation speeds for these different plots, going from 50 hertz all the way up to 300 hertz. And just to sort of clarify, the flagellar motor on its own goes somewhere between 200 and 300 hertz. So what we can actually do in this experiment is drive it faster than it wants to go on its own. And what we see is something really interesting, which is that the response of the motor really depends on the electrorotation speed at which we drive the motor. Up to about 150 hertz, we see that nothing much happens. And above 150 hertz, we see a very strong electrorotation speed dependent response. So what's going on here? And to understand this result, we have to go back to this torque speed relationship that I showed you earlier, which tells us how much torque the motor produces at different speeds. So what we are doing when we are increasing the electrorotation speed is that we are reducing motor torque. And this reduction in torque is what then leads to this remodeling kinetics that we see. In fact, it matches very nicely with the data because the torque decreases only once we are past this plateau region, which happens at about 130 hertz. So this is consistent with the fact that we don't really see any remodeling below about 150 hertz. So that leads to this very clear hypothesis that stator remodeling depends on the torque produced by these stator units. To really probe this hypothesis, then we built a very simple quantitative model for stator assembly, which is shown here. So we assume that the motor has a fixed number of sites on which the stator units can bind, which is given by capital N. At any point, say small n number of those sites are occupied by bound stator units. And then we assume that the unbound units can actually bind the motor with an on rate K plus, and the bound units can leave with an off rate K minus. And this simple picture that I just described can be written down in a very simple first order kinetics differential equation. And so we fit this simple model to our data that I showed you before, and we find that this very simple model does a pretty good job at fitting the data. And by doing this fitting, we can then extract the on and the off rates for stator units binding the motor. So the result of this analysis is shown here, where I'm showing now the rates on the y-axis as a function of torque produced by those stator units on the x-axis. And consistent with our hypothesis, we see that the rates do change with torque. In fact, what we find is that the on rate shown by these filled symbols stays more or less constant, while the off rate decreases with torque. So this is suggesting that somehow torque production by these stator units stabilizes their binding to the motor, which means that at higher torque, somehow their binding is more stable, so they're less likely to unbind, decreasing this off rate. And that lends itself really nicely to this picture of a free energy landscape, if you will, of the stator binding, which what I'm showing here is the free energy as a function of whether the unit is bound or unbound, shown by this schematic on top. And what we believe is that in the at low torque, the bound state has a higher free energy than the unbound state, which means that it is actually less favorable. And what we think may be happening is that the production of torque is reducing the free energy of the bound state, making it more and more favorable. In fact, we can calculate from the rates that we have measured, we can calculate the free energy difference between the bound and the unbound states, which is shown here on the right. So here I have the free energy difference on the y-axis as a function of torque produced by stator units on the x-axis. And what we see is two things. One, that inconsistent with this picture that I show on the left, the free energy indeed decreases with the torque. The free energy difference decreases the torque. Not only that, it decreases in a very specific manner. It decreases linearly with torque. And if we translate that to this, how the free energy depends on the rates, and assuming that the on rate stays constant, this would indicate that the off rate decreases exponentially with torque, which is exactly what we find in our data. So combining together these ideas gives us basically a picture for what could be happening at the molecular scale. What we think is, this is our working model. What we think is happening at low torque, the part of the stator unit that binds the peptidoglycan is in a relaxed state, and that makes it more likely to unbind. But when the motor produces high torque at increased load, these parts are mechanically stretched, and that stretching makes somehow this binding between the mode A and the peptidoglycan more stable, makes them more unlikely to bind, unlikely to unbind, and that increases their number over time. And to take it one step further, we actually wanted to also test this model, and then again going back to this torque speed curve and how there is an anisotropy between the clockwise and counterclockwise motors allows us to test this model quantitatively, because we know that the clockwise motor produces much smaller torque than the counterclockwise motor. So if we do the same experiment on clockwise motors and then compare the data, we can test this model. So we did that, and in the plots here, I'm showing you just the summary of a lot of experiments. It's just going into the rates as a function of torque and the free energy difference as a function of torque. And quite satisfactorily, we see that the two sets of data from clockwise and counterclockwise motors collapse right on top of each other, but only if you plot them as a function of torque. So sort of validating our original model. So just to wrap up here, what I've hopefully showed you, I've convinced you, is that the flagellar motor has this feature which is similar to an automatic gear shift of cars, in which at high load, the force-producing stator units, force-producing stator complex is composed of many stator units, which are released at low load and gained again if the load goes high again, allowing it to adapt to this changing mechanical environments. And I also want to take a moment to sort of think again about this analogy between a car and a bacterial motor. So as I've shown, there's quite a lot of similarity. Both of them are able to adapt to mechanical load, but they do that in actually a very different way. Cars change, the automatic gear shift in a car changes the transmission between the engine and the wheels to change the torque. But what happens in the flagellar motor, as we have seen, is that it changes the engine itself. It's sort of the equivalent of adding or removing pistons from a car as this load increases or decreases. And since this is an ocean biophysics group, I also wanted to sort of take a moment to think about the ecological relevance of, other than being able to adapt to mechanical environments and save energy or some and things like that. And there are indications of how this load-dependent remodeling could be actually relevant in natural environments. One of which is this. Actually, all of them have to do with interaction with surfaces. So we know, for example, from this classic experiment that bacteria get trapped in the vicinity of surfaces because of hydrodynamic forces. And we also know that in the vicinity of surfaces, the flagellum actually experiences a higher load. So this could be a way for the motor to adapt to that change in load and be able to perhaps free itself from being trapped near a surface. And another situation, again, close to surface where this would be relevant is during bacterial swarming, where bacteria actually accumulate on top of surfaces in very high cell density in very crowded environments. And you can imagine that this can also lead to dramatic increase in the load experienced by the flagella of these motors. And the final sort of part of this story is that the motor most likely participates in surface sensing before biofilm formation. For example, when free swimming cells interact with surfaces, they somehow sense this presence of surface, and oftentimes they decide to settle down and form biofilms. And how does the cell know that it's on a surface? And there's a lot of evidence pointing to the direction of the flagellar motor, that the increased load on the filament in the vicinity of a surface actually provides a signal to the cell that it is on a surface, that it should do something and maybe settle down. With that, I think I will just wrap up. Thank all my collaborators, members of my lab, and my funding from NIH. And here are just a few references if you want to check out this work more. And I also just wanted to advertise that I will be looking for faculty positions in 2022. So if your department is looking for someone looking to hire faculty, and if you think I could be a good fit, please let me know. Yeah, and thank you all for being here, despite many of you in a very difficult time zone. So we can have some discussion and questions if you like.
Thank you, Navish, and let's, I guess, virtually applaud for him. And I was like, I didn't get to give an introduction at the beginning because you jumped right into your talk. And so I was just going to give a little bit of your background before we get into the Q&A. So yeah. He, you know, got his PhD at the Technical University of Denmark and is currently at Harvard University in the Berg Lab. As he just said, he has also spent some time at the Indian Institute of Technology and the National Center for Biological Sciences in India, as well as at Virginia Tech and the Cold Spring Harbor Laboratories and the Marine Biological Laboratory at Woods Hole in the United States. And we were really excited to have you speak today, and I really enjoyed your talk. And so now I will open the floor to some questions. Johannes, you had a couple. Would you like to start?
Yes, thank you, Navish, for an interesting talk. I'm Johannes from ETH Zurich. I'm a postdoctoral in the Doctor's Lab. Hey, yeah, basically, my questions in the chat are basically about differences, if any, with the motors that we find in marine bacteria that are driven by ions. So my first question is, maybe this is known, is this relationship between sort of speed and torque the same for those motors, or is this different?
So just, yeah, go ahead.
Yeah, and the second thing is about this ecological relevance. Would you expect there that this is maybe different for E. coli that tries to sort of keep the swimming speed constant, and these marine bacteria that frequently seem to switch between different speeds?
Right. Okay, so let's, your first question was if the relationship between the torque output and speed is the same for marine bacteria, which often use different ions as energy sources. Is that correct, Johannes?
Yes, that's correct.
Yeah. So there have not been a lot of measurements of bacteria using different energy sources. There have been most of the laboratory biophysical measurements have been made using E. coli, Salmonella, and a couple others. But I believe that there are actually measurements from Richard Berry's group at Oxford where they have found that the this very specific two-phase torque speed curve is actually also found in bacteria that use sodium ions as an energy source. So yes, there is a little bit of evidence that this is actually the same. The torque speed relationship is similar in marine bacteria, although they drive their motors at actually a much larger speed and they produce much larger torque